In today's lesson, we are going to be looking at compound and simple interest. So this is going to be a little bit of a review as we begin in our finance unit. So first, an application of an exponential model is finding the accumulated amount of interest on an investment. So we are kind of looking at exponential models in this case, specifically when we're trying to find out how much interest we're earning on an investment. So we have an example, the interest rate is 5% per year, and we want to determine the amount at the end of each year. So we're going to be looking at two scenarios, simple interest and compound interest. So simple interest is interest based only on the principal loan or investment, and compound interest is interest based on the principal amount and the accumulated interest. So we're going to look at them in general, kind of in the basic form, and then we're going to look at an actual formula to help us solve some questions. So if we go through simple interest first, essentially each year we're only looking at, or each year one, we have $100. We earn 5% interest, so $5. So the amount in the account is $105. The next year, the interest earned is again $5, same as the year before, because we're only earning interest on the principal amount, which is the initial value. So then year three, we have $110. That year, we only earn $5, and we end with $115. And again, we would earn $5 that year as well, and so on. So after 4 years, or after 3 years technically of earning interest, a total of $115. Compound interest is a little different because even though the first year is the same, we still earn the 5%, which means in that year we have $105. The interest is now 5% on that new amount, so on 105. So we actually earn $5 and an extra 25 cents in that second year. So year three, we have 110.25, and then the interest being earned is 5% on top or on that amount, so on the 1025. So we earn $5.51. That means then in year four, we have 115.76. And again, in year four, we would earn 5% on the new amount because it's the principal amount plus the accumulated interest. So 5% times 115.76. And in that fourth year, we would earn $5.79. So we're already earned almost close to an extra dollar after those 4 years of saving money. And where in the previous one, in simple interest, we only would have earned $5 throughout. It wouldn't have changed. So after the 4 years of compound interest, we are earning almost roughly $1.54 more than the simple interest formula. And the two graphs here show the different types of investments. Right? We can see the simple interest in black. And we can see the compound interest in blue. So which one do you think you would rather have an investment in? The simple interest or the compound interest after 15 years if you put $100 in the bank? Are you going to say the simple interest just because it's easier to calculate? Or compound interest because it's going to give you more money in the end? I think most people would say probably the one that gives us more money. And realistically, most accounts, most savings deal in compound interest over simple interest because it does give you more money. It just tends to be the more common type of interest. Because on that end, if it earns you more money if you're saving, it would also cost you more money if you're borrowing. So that's the reason why it is used, because they'll tend to make more money back when you borrow money compared to how much they would actually have to give out in terms of loans. So compound interest is the general type of interest that's used. So that is what we're primarily going to focus on. So there is a formula to calculate compound interest that we don't have to go through and calculate it each year, add it to our new amount, calculate the percent again, add it to our new amount, and so on and so on. And it does allow us to do a few different things. So our formula for compound interest is A equals P times 1 plus I to the power of n. A is the amount at the end of n periods. You might also call it the future value, what we're going to have in the end. P is the principal invested into the account or borrowed. So it's the initial amount that we're having. I is the interest rate per period. And so the per period is key because we do have to do a small calculation. So for I, we take the annual interest rate. So we'll be given an interest rate that's usually an annual interest rate, but then it's usually divided up into number of periods or compounding periods. So that means when do they calculate the interest? So there's different scenarios that you may come across depending on what situation you're in. N is the number of years times the number of periods per year to give us how many compounding periods do we have in total. So how many times are we calculating interest over our savings or over our loan? So those two calculations require the number of periods. And the number of compound periods depends on the wording that's used. So if it's yearly, we have one compounding period. So every year they calculate the interest and it gets added on. Very similar to the warm-up kind of we just did that table. Semi-annually means twice a year. So twice a year, your interest is calculated and added on to your principal amount. So you earn a little bit more each year. Quarterly, that yearly amount is compounded quarterly, so it's broken up into 4 periods. So they calculate the amount of interest you earned 4 times a year. Monthly would be 12, daily would be 365, weekly would be 52, bi-weekly would be 26, right? So different scenarios basically just comes down to how many of these time periods are in a year. So let's look at a couple of examples. So Gina wants to invest $2,500 in an investment that earns 6.5% compounded yearly. What will the investment be worth after 5 years? So because we're looking for the future value, we are going to be looking for A. P is our present value or our principal, so 25,000 or 2,500. Our interest is 0.065 or 6.5%. But we do have to do a calculation. We have to divide it by the number of compounding periods, which in this case, because it says compounding yearly, this means 1 compounding period. So this does make our calculations relatively simple because it's 0.065 divided by 1, which is 0.065. For n, the number of years, 5 times the compounding period, which is 1, which equals 5. So not too much extra calculation that we had to do there. We can then go into our formula. So A equals P times 1 plus I to the power of n. So we have 2,500 times 1 plus 0.065 to the power of 5. Now you can simplify inside the brackets first if you want. 1.065 to the power of 5. Depending on your calculator, it may be easier to do that first. Remember, we have to follow BEDMAS, so we have to do the exponent first. So we have to do the 1.065 to the power of 5 first, and then multiply by the principal. Right? You're not multiplying the principal and then raising it to the exponent. You're doing the exponent first and then multiplying. So $3,425.22 is going to be our future amount, or what our investment is worth after 5 years. Again, make sure you're rounding to two decimal places. We are dealing with money, so we can have two decimal places. So make sure you're rounding there. So that is how much money we would have after 5 years based on this scenario. Next example, Cody is borrowing $3,000 to buy a car. The bank will give him a loan at a rate of 8% compounded quarterly for 4 years. If he doesn't pay back the loan in 3 years, how much money will he owe? So again, we're looking for the future amount. So if he doesn't pay it back in 3 years, how much money will he owe? So the future value, we don't know. I think we have a typo here. Should be, if he doesn't pay the loan back after 4 years. So let's just change that. So 4 years, how much money will he owe? So principal, we're starting off borrowing $3,000. The interest, it's 8% compounded quarterly. So this compounding period here, or this term, means 4 compounding periods. So 4 compounding periods, so we have to take our rate, divide it by 4 to get our I value, so 0.02. We're then going to take the 4 years, multiply it by 4, because there's 4 compounding periods in a year, and we get 16, so there's 16 compounding periods in total. Now that we have all our values, we can plug it into our formula. So 3,000 times 1 plus 0.02 to the power of 16. Again, we can simplify 1.02 to the power of 16. And when we solve, remember to do the exponent first. So 1.02 to the power of 16. And then multiply that by 3,000. So you should get $4,118.36. So again, that means that after 4 years, if he doesn't pay back the loan, he's going to owe $4,000 or $4,118.36. So an extra $1,000 if he doesn't pay back his loan. The other situation that we may come across with interest or compound interest is the present value. Maybe we know how much we want to have. We want to know, based on the given scenario, how much do we have to invest? Right? This might be more applicable if you're saving up for something. You know what your accounts, the rates on your accounts are. So now you're just kind of determining, okay, how much do I have to put in, or how much do I have to have at first? So same values. PV is the present value, how much you need today. A is the accumulated amount, or the future amount, so how much we plan on having. 1 is just part of the equation. I is still the interest rate per period, which we calculate by dividing the rate, annual rate, by the number of periods. And it's raised to the power of negative n, which is the number of years, again, times the number of periods per year. So if we go through an example, so Michelle's grandparents want to retire with $150,000 in the bank in 9 years from now. How much should they invest now at an interest rate of 5.75% per year, or per annum, which just means year, compounded quarterly? So we don't know what our present value is. We do know that our future value is 150,000. The I is 0.0575, but because it's compounded quarterly, which means 4 compounding periods, we take that rate and divide it by 4. We get 0.014375. And for n, we take 9 years, multiply by 4 periods per year, which gives us 36 total compounding periods. Now, you might be tempted to round that I value. I would not, because by rounding it, you may actually lose out or get an incorrect amount of money that you might have to save. Right? So you want to keep the exact value. So our present value is going to equal a times 1 plus I to the power of negative n. So 1,500 or 150,000 times 1 plus 0.014375 to the power of negative 36. So again, we can simplify that bracket. 1.014375 to the power of negative 36. Again, remember to do that exponent first. So 1.014375 to the power of negative 36. And then multiply that by the future amount. And we get a present value of 89,731.29. So if they wanted to have $150,000 in 9 years, they need to invest close to $90,000 now so that they get that, which isn't too bad because you're making almost $60,000 in interest over 9 years. So if you could find that rate and save it at that, that's not too bad. That's not a bad increase in your investment. The next example, Leon's offers a furniture set for $2,500 payable in 2 years. The loan bank rate is 9.5% compounded monthly. What is the discounted rate if I pay it off now on the purchase? So if I didn't have to pay, so that's the $25,000 at the end of the 2 years. So the interest is put into that. If I wanted to pay it off now, what would it actually be? So if I have to take off those interest payments, essentially. So I don't know my present value. I know my future value is the $2,500. The interest is 0.095, but because it's compounded monthly, I need to divide by 12. Throw that in there. So there's 12 compounding periods. So 0.095 divided by 12, 0.0079167. And then it's 2 years times 12, so it gives us 24 total compounding periods over that time. So our present value, we're going to determine that by taking the future amount, multiplying it by 1 plus, formula, mixing it up. So future amount multiplied by 1 plus I to the power of negative n. So 2,500 times 1 plus 0.0079167 to the power of negative 24. So again, let's simplify the brackets. 1 plus, or 1.0079167, power of negative 24. We want to do the exponent first. So that 1.0079167 to the power of negative 24, and then multiply that by your future amount, and you should have 2,068.94. So that is how much you could save, or that's the discounted value if you paid it off now. So that would be the price, not taking into consideration any of the interest that you would build up due to taking out a loan and paying it off at the end of 2 years. So it might be better value. If you have the money, it might be a better value to pay it off now rather than pay an extra $432 roughly, $31 to pay it off over the 2 years. So again, the main thing is just looking a little bit at the difference between compound and simple interest, and then primarily focusing on two compound interest formulas. One, just calculating the compound interest in general, and then using that in kind of the reverse to find what the present value would be. So just using the compound interest formula to find the future value and the present value. Again, that should be a little bit of review from last year, so hopefully it wasn't too bad. Again, make sure you understand what the different parts of the formula are and how you can find them from the question. And essentially, you're just plugging them in and doing a calculation.